Okay, so as you can see from the title of the video, we're going to be looking at integration. Now, integration is basically the process of finding a function from its derivative, and in this process we reverse the operation of differentiating. Being that we're going to find a function from its derivative, we just reverse differentiation in order to find that function, and that is simply what integration is: reversing differentiation. Now, when we integrate, we find the integral, right? And it's also called the antiderivative. And as I said before, it's reversing the process of differentiation, so hence antiderivative. So let's just get straight into it. So let's say we have f prime of x, right? Now we get f prime of x when we differentiate f of x. So we write it here. So d dx of f of x gives us f prime of x. Now, if we should integrate f prime of x, with respect to x, then simply we'll get f of x. Good. Now, when we integrate, we usually add a constant of integration, and I'll explain why in a bit. Now, in a future video, I'll talk about definite and indefinite integrals. Now, since we are here, I'm just going to mention that this is basically an indefinite integral because we do not have any limits in which we're going to integrate between. So as I said, I will cover that in a future video. For now, let's just stick with this. So we integrate f prime of x and we get f of x. That's just saying if you integrate the derivative of a function, then you should get the function, right? So when we integrate, in order to find a function, we're integrating the derivative of that function. Good. So let me put an example here. Let's say we differentiate x squared. So we differentiate x squared, and as you can see here, while explaining things, I make mention to differentiation because integration is basically the opposite. So differentiation helps to understand integration. Okay, so if we differentiate x squared, as we know from the what we call the power rule, you multiply by the power and you reduce the power by 1, so that's just 2x, right? Now we're saying if we integrate 2x with respect to x, then we're supposed to get x squared. Now, as I said before, when we integrate, we add a constant, right? Reason being, 2x could be the derivative of, let me just write it here. So let's say we're asked to differentiate x squared plus 3, then that is 2x, right? Because if we integrate x squared, we're going to get, if we differentiate x squared, we're going to get 2x, and if we differentiate 3, we're going to get 0. So 2x is the derivative of x squared plus 3. Also, 2x is the derivative of x squared by itself. If we should differentiate x squared plus 10, look here, you have it again, the derivative is also 2x. So what we're saying is, when we integrate 2x, yes, we're going to get x squared, but just writing x squared does not account for the possible constant that the original function may have, right? So we add a constant in order to account for that. Okay, let me just erase here. Good. Okay, continuing. So let me just write another problem here. X squared. Great. Cool. So let's say we're asked to integrate x squared with respect to x. Now, if we think of differentiation, then we're going to say, okay, so how could I have gotten an x squared when I differentiate, right? So what could I differentiate in order to get an x squared? And if you haven't thought of it already, then that's an x cubed. Great. So if we should differentiate x cubed, we're going to get 3x squared. Now, we have accounted for the x squared, right? But the 3 here we haven't yet accounted for. So let me just come back up here. So if we integrate x squared, yes, we should have an x cubed in our answer. But remember, if you differentiate x cubed, you get a 3x squared. Now, since a 3 wasn't present out here, then what we can simply do is divide by a 3 there. So therefore, let me just erase this, and I'm doing this so you can basically have a better understanding of the thought process. So okay, so we integrate x squared where we are supposed to get x cubed, but remember, if we differentiate x cubed, then we get 3x squared, and as I mentioned before, a 3 wasn't in that problem. So in order to basically cancel out that 3 that wasn't there, then we would divide by a 3. So let's differentiate our answer there, and of course remember to put your plus c there. Okay, so let me continue. Right, so if we should differentiate, because this is how we test if our integral, so I said the result here is called the integral, this is how we test if our integral was indeed correct. and we can put the c here. The c is a constant. As you know, you differentiate a constant, that's 0, so it doesn't really matter. Okay, so if as you know from differentiation, we keep the coefficient there, and we basically differentiate the x cubed. Now 1/3 would be the coefficient. Now we differentiate the x cubed. When we differentiate x cubed, we get 3x squared. When you differentiate c, that's 0, so that's that. Now if we look here, we realize that 1/3 cancels with the 3. 1/3 times 3, that's 1. So we can see that x cubed divided by 3 was indeed our correct answer, because we get back our x squared. Now let's try another problem, and then we can simply write a general rule for this. Now let's say we're asked to integrate 4x cubed. Good. With respect to x, of course. So look at the problem again and ask ourselves, what would we differentiate in order to get an x cubed? And simply put, that must be x to the 4th, because if you differentiate x to the 4th, when you reduce the power by 1, you're going to get an x cubed. Now in this particular problem, we have to integrate 4x cubed. Now if we should differentiate x to the 4th, which is in our result right there, if we should differentiate x to the 4th, you notice that that answer is 4x cubed. So since the question was asking us to integrate 4x cubed, then the integral of 4x cubed is simply 4, because the integral of 4x cubed is simply x to the 4th, sorry, because if we differentiate x to the 4th, then we get 4x cubed. And of course you add your constant of integration. Let me just write another example. Great. Let's say we had 3x to the 5th power. Good. Dx. Now again we ask ourselves, what power of x do we differentiate in order to get x to the 5th? And that's, of course, that is x to the 6th. But if we differentiate x to the 6th, then we are going to get 6x to the 5th power. Look, so if we have dx of x to the 5th, sorry, x to the 6th power, then we're going to get 6x to the 5th power. Good. So in this particular problem, we do not have 6x to the 5th power. We actually have 3x to the 5th power. So basically what happened is we halved the 6 in order to get 3x to the 5th power. So that's basically what happened to this here. We just half it in order to get the correct answer. If we test it here, dx of x to the 6th over 2, so we keep the constant, the coefficient I should say. When we differentiate x to the 6th, what we get is 6x to the 5th power, and half of 6x to the fifth is 3x to the fifth power, which is what we have here to integrate. So therefore, since we differentiated x to the 6 divided by 2 and got 3x to the fifth, then that means if we should integrate 3x to the fifth, we should get back x to the sixth over 2. And of course, we add our constant of integration plus c. Now that does not have to be plus c, we could have plus k, plus b, but by convention we use plus c or plus k. Okay, so now let me just write a general rule. So that rule, and that is when we're integrating x to some power. So if we have the integral of x to the n with respect to x, then that's simply x to the n plus 1, and we divide by the new power. Good. So let's say we had x cubed. If we were to integrate x cubed with respect to x, then that's simply x to the 3 plus 1 power, if we're following from that formula up there, over 3 plus 1, because our n would be 3, so we basically add 1 to 3 and divide by 3 plus 1, and that's simply x to the 4th over 4. Good. So it's one rule down. Let's say we are asked to integrate a constant with respect to x. C is just some constant. Then that's basically cx. And guys, remember, let me just use k in this instance since I already have a c there. Don't want any confusions. So that's basically the constant. Integrating the constant is basically the constant times x, and you add your constant of integration. Good. So if we should integrate 3 with respect to x, then that's simply 3x plus c. If we should integrate e with respect to x, and just in case you didn't know before, e is a constant. It's approximately 2.718 if memory serves. Okay, so if we integrate e, which is a constant, we're supposed to get e times x plus c. Right. If we should integrate pi with respect to x, that's basically pi x plus our constant of integration. So yeah, that's basically how we integrate powers of x and how we integrate constants. Now we are going to come across other types of problems to integrate. We're going to come across logs, exponents, products, which will be covered throughout the course of this series. I'm going to make a series of videos on integration, because making one video would be really long, so I'm going to make a series. So let's see, we had something like this to integrate: x cubed plus x squared plus 3x plus 6. Now how we integrate a problem like this is basically by integrating each term. So if we integrate x cubed based on this formula up here, we should get x to the 4th divided by 4, and that's plus. Now we integrate x squared, so basically we're integrating each term and then we add them. So that's the integral of x squared, that's x cubed over 3 plus the integral of 3x, that's 3x squared over 2, and the integral of 6, that's 6x, and of course we have our plus c, right? And that's just how we integrate a problem like this. Now, no matter what appears here after the integral sign, be it sin x plus cos x plus x cubed plus x squared, with respect to x, what we do is simply integrate each term and add them. Okay, so we can write a general rule for that. So let's say we have the integral of f of x plus g of x. This is basically how you can think about each term. You can think about each term as being separate functions, and we integrate with respect to x. That's basically the integral of f of x plus the integral of g of x. And remember, these are with respect to x. So as I said, you simply integrate each term and you add the result. So let me just rewrite another example. If we had 3x minus 6x cubed with respect to x, that's basically 3x squared upon 2. When we integrate 3x, that's what we should get. Then we simply integrate the next term and add whatever we got for that integral. So if we integrate negative 6x cubed, we're supposed to get negative 6x to the 4th power over 4. Great. And of course we can simplify this improper fraction here, so that would be 3x to the 4th over 2. That's if you really want to simplify that. and of course remember your plus c. Now let me write down the integrals of some stuff that you should know. So for instance, the integral of sine x with respect to x, that's negative cos x plus k. If we integrate the cosine of x with respect to x, then we're supposed to get sine x plus some constant. Okay, so of course we can check if this is correct. So as I said before, differentiation is the opposite of integration and vice versa. So if we integrate sine x and got negative cos x, then differentiating negative cos x should give us our sine x. So let's just go ahead and go off to the side here and differentiate negative cos x. And as you know, you can keep negative 1 there, and we basically differentiate cos x. So when you differentiate cos x, you're supposed to get negative sine x. Good. Now negative 1 times negative sine x, that's basically sine x. So as we can see, if we differentiate negative cos x, we get sine x. Therefore, if we integrate sine x, we should get negative cos x. Same with down here. If you differentiate sine x, you get the cosine of x. Therefore, if you integrate the cosine of x, you should get sine x. Good. Okay. Okay, let me write this here. If we integrate 1 upon x dx, we should get the natural log of x plus some constant. Okay, now let me just and be sure that you remember these. Now let me just write a example problem here, an example problem. So let's say we had to integrate x to the negative 2 power, right, dx. If we remember our laws of indices, we should know that that's basically the integral of 1 over x squared, great, with respect to x. Okay, I'm just mentioning that is if you got the problem like this, you can translate it to that. Okay, so let me just clear this for now. Okay, good. So in solving this problem, we can follow this formula up here. It states that we add 1 to the power, so -2 plus 1, and then we simply divide by the new power, okay, and we add our constant. So that's basically x to the -1 over -1, and that's basically -x to the -1 power. Or we can apply our indices knowledge and rewrite that as -1 over x. Either way doesn't really matter, it's the correct answer. Now let me just clear the screen again. We may, even though I wrote this before, I'm just going to dive in a little. Okay, so if we got that problem, even though I wrote the answer before, just bear with me. Okay, so we have that problem, the integral of 1 over x, and of course we should know that that's basically the integral of x to the -1 power. Now we may be inclined to use this basic formula up here. Now let's see what happens when we do that. So if we are going to write back our x and x to the -1 plus 1, and we divide by -1 plus 1, and of course we add our k, right? That's what we would be thinking. Now look what happens here. We have x to the 0 power divided by 0. Now that is where the problem comes in, because if you didn't know before, you cannot divide by 0. That's indeterminate. So therefore doing that is not correct. Okay, let me write about that. And the integral of 1 over x, or x to the -1, is simply ln x plus k. Now we can test that. If you recall from my videos on differentiation, where I covered differentiating logarithmic functions, then you would know that when you differentiate ln x, that's basically 1 over x. Good. And if you haven't already watched my videos on differentiation, you can go and check them out. So if we differentiate ln x and get 1 over x, then we should integrate 1 over x and get ln x. Let me just write another problem here. Let's say we get x to the -3 dx. Good. Then that's simply x x to the minus 3 plus 1 over minus 3 plus 1 plus our constant, and that's simply x to the minus 2 over minus 2. Good. Okay, so since I mentioned the integral of sine x and cosine x, let me write an example problem here. Let's say we have x cubed plus sine x minus cos x. Good. Now with respect to x, and if you can recall, we simply integrate each term. So if we integrate x cubed, then that's x to the 4th based on this formula up here over 4. And if you can recall, when you integrate sine x, that's negative cos x, and we have our minus sign there. When we integrate cos x, we get sin x, and we have our constant of integration. So let's tidy this up. So that's x to the 4th over 4 minus cos x minus sin x plus k. Good. Now I'm going to write another problem. Integral of and that's simply negative cos x minus x cubed upon 3. Good. Plus our constant. Now let me just dive in a little deeper. Okay, let's say we had something of this sort. The integral of and I probably should have led with this, but that's not a problem. Okay, so in a case like this, that's basically ln f of x plus our constant of integration. Now remember, from my videos on differentiation, again, if you haven't checked them out, please go and check them out. If we should differentiate ln f of x, then we're going to get 1 upon f of x multiplied by the derivative of f of x, which is f prime of x. So therefore, if we, let me just, good. So if we integrate f prime of x upon f of x, then we should get ln f of x. Good, so I can put an example here. Let's say we have upon x squared plus x. Good. Now our job in a case like this is to identify whether or not the numerator is the derivative of the denominator. And as we can see, if we should differentiate the denominator, we would get 2x plus 1. And if we look at the numerator, it is 2x plus 1. So therefore, this is simply the natural log of x squared plus x, and we add our constant of integration. Good. And I think I'm going to end the video here. Let me just add another problem. The dogs are really noisy. Okay, let's say we had the integral of tan x. Okay, good. Let me just use a negative tan x. Negative tan x dx. Now I'm going to mention something I haven't mentioned before in my previous videos, I think, and that is tan x. Let me write it up here. Tan x is equal to sine x upon the cosine of x. Good. So therefore we can rewrite this as negative of my pen is giving me some problems here. Okay, so that's sine x upon cos x. Good. Now what we need to ask ourselves is the numerator the derivative of the denominator? And if we differentiate the denominator, which is cos x, we're going to get negative sine x. Now since there is a negative sign here, and this being a fraction, the negative sign can either go in the numerator or the denominator. We're going to put it in the numerator. Good. And as I said, if you differentiate cos x, you get negative sine x. Now since we have negative sine x in the numerator, then we can confirm that the numerator is the derivative of the denominator. Hence the integral is simply ln cos x plus k. And one thing to note is when you write the integral of these types of functions where you have ln, it's always good to use the modulus sign. These lines mean the modulus of the cosine of x. What that simply means is it takes all the positive values, only positive values, being that you cannot find the log of a negative number, so using the modulus sign ensures that only positive numbers are passed into the natural log function, right? Okay. And up here you can also use those brackets. In some cases it's clearly not needed, but for now let's just keep that. And also in our general formula here, just making sure that I mention this. Okay, good. So now that I have finished that example, let's just end the video here, and I'll continue in another video.